The 3-meter long, 100-kilogram rigid beam shown above, or shown below, is supported at each end. An 80-kilogram student stands 2 meters from one support. How much upward force does each support exert on the beam? Okay, so our givens, the length of the beam is equal to 3 meters. Let's say R of the student is equal to 2 meters. The mass of the beam is equal to 100 kilograms, and the mass of the student is equal to 80 kilograms. And we need to find F1 and F2. We'll label those. So we're going to say that the force here, this is F1, and this force right here is going to be F2. We're also going to label, well, let's do an extended free body diagram. So we're going to have a board here. Our center of mass is going to be right here. So we're going to have a force up. This is force 1, and this is really a normal force. And this is force 2, another normal force. This right here, we're going to have a force down, and this is the force of the beam, or from due to gravity. And then we're going to have a force up over here for the student. So it's going to be down. So force here, down, and we'll call that F of the student. Okay, so in a problem like this where we're really looking at balancing forces and balancing torques. So the two things we're going to be doing is we're looking at the sum of the forces is equal to 0, and the sum of the torques are equal to 0. Right, and what the sum of the forces means is that my object is not moving up or down. It's static, and then sum of the torques means my object isn't rotating. So each of these forces would cause a rotation, but we're balancing it, so we need to make sure they're balanced, and the net torque is equal to 0. So let's write out the sum of the forces first. So we have F1 plus F2, they're both in the up direction, and then minus FB minus Fs is equal to 0. And so just writing this out further, F1 plus F2 minus force of the beam is just M of the beam times G, and then force of the student is just M of the student times G is equal to 0. And now the sum of the torques. So the first thing we do with a torque problem is we pick a pivot point. And I'm going to pick this right here at F1 as my pivot point. And the reason I'm doing that is because I don't know F1 and F2. I have enough information to find the force of the beam and the force of the student, but I don't have enough information to find F1 or F2. So if I can make one of the unknowns my pivot point, it really helps, because then I'll only have F2 in this torque equation, and I can then solve for F2 and then eventually plug it back into this F2 right here. So that's what I'm going to do. I'm going to set F1, the pivot point here, equal to 0. And so I'll show you why that's advantageous. So remember, my torque is R cross F. Torque is equal to R cross F, right? And remember, that's RF sine theta. And sine each of these forces, if I pick my pivot point here, each of these forces is, I can define my R. So R for F2 or FB, I would go here. This would be, or maybe I'll make it red. This would be my R for the beam. I'll make this one blue. This would be my R for the student. And then let's see if I can pick green maybe. So green will be my R for F2. And you can see for each one of these, the R and F, so I'm going to call this FR2. I'm going to call with my blue. This is going to be R of the student. So each one of these is perpendicular. So R and F are perpendicular for each one. But what about direction? So I'm looking now for direction. So notice that my FB here is going to when I exert a force on the beam down, it's going to cause my beam to rotate around the pivot point, and it's going to cause it to rotate like this. And so that's clockwise. So that's going to be a negative term. Same thing with the student. The student, when you add the force, when you exert a force at this position down, it's going to rotate clockwise again around the pivot point. But for F2, when I exert a force F2 up, I'm going to have a counterclockwise rotation around the pivot point. And so that's the one I'm going to start with because it's positive. So I'm going to say F2 times R2, and then minus FB times RB minus FS RS. And now looking at F1 would be going this way. So we're going to make that a negative. So that's going to be minus F1 R1 equals 0. But now my R1 is equal to 0 because the R is the distance, the forces from my pivot point. And since my force is right on my pivot point, that term goes away. So now I can plug in. So I have F2. Now R2 is equal to just the length, the L of the beam. So I'm going to have F2L minus FB is going to be the mass of the beam times G. And R of the beam is going to be L over 2 because this is the beam. We're thinking about it as the mass is uniformly distributed, so I can think of all of the mass being centered at the center of the beam, so that's why I put it as L over 2. And then minus the student would be the mass of the student times G, and we're going to keep that as RS, and we'll plug in the number in just a bit. All right, so what I'm solving for here is I'm going to solve for F2. So I can find F2, that's one of the things that they asked me to find in the problem. And then after that, I can plug my F2 into my sum of the forces equation to get F1. So F2, let's do F2L is equal to, I can add these terms to both sides, and I get F2L is equal to M of the beam, G, L over 2, minus mass of the student, G, RS. So I can find F2 by just dividing both sides by L. So I'm going to have MBG L over 2 divided by L minus MSG RS over L. So here my L's cancel. And now I can just plug in. So F2 is equal to the mass of the beam is 100 kilograms times 9.8 meters per second squared divided by 2. And minus the mass of the student is 80 kilograms times 9.8 meters per second squared times 2 meters, because I know from my givens my RS is 2 meters, and divided by 3 meters. I'm going to plug this into, it's already in my MATLAB, but I think I did one of the equations wrong. So let's just go back and check. Oh, that's not what I wanted to do. Hopefully it won't open it a third time. Okay, so we can just go here to this MATLAB and here. So 100 times 9.8, so divide by 2 here. And we get 767.7. So 7, we'll go back here, and so F2 equal to 767.7 newtons. And now I can take this and plug it in right up here. So I want to plug that in so I can find F1. So F1 is going to equal, I can add MBG and MSG to both sides. So I'm going to have MBG plus MSG and minus F2. So I'm going to have F1 is equal to, I can factor the G out. So that's 9.8 meters per second squared. And then I'm going to have mass of the beam is 100 and mass of the student is 80. So I'm going to have 180 kilograms minus 767.7 newtons. So do that math. Go. So I just look and see. That's 9.8 times 180 minus the answer, and we get 996.3. Oh, let's see. We'll do it that way. Let's just double check. 996.3. Okay. So F1 is equal to 996.3 newtons. So these are the forces that I get that are provided by the supports right on this beam in order to hold up the beam and also hold up the person that's standing on it.